So in this case, L is not 0. We have some holography at the ODE. That change the structure of T system, as I mentioned in previous. So if we take the Wronskian of the Y0 to this spaces, this to psi plus minus 1. So we can define some so-called Q function. Due to the some semantic rotation property of the solution, we will have some the yk, the Wronskian of the yk and psi plus minus 1 had some shifting. We have other phases. Then we plug into that definition with the some y minus 1 is expressed with the y0 and y1, the respective spaces. We will have the relation between t and q functions. So this is called the Maxwell TQ relations, which is also appears in the integral. So if we are consider the so for example harmonic oscillator case, where E is some real and positive eigenvalue of the differential equation. So we have no longer the linear independence of the two solutions, y0 and y1. So then, in that case, the T function must vanish. So then it will constrain the solution structure of the Q function. So this function is called the beta equation in the context of integral. So actually, this is the beta under equation of the twisted six part. So Y systems, we can derive some physical quantities from that Y system. So this is called some dynamic beta. I will not explain this much. But just roughly, we will have some logarithmic of the Y function define some pseudo energy. So E is theta is defined by this from this energy. So from the Y system, we can show that the this pseudo energy obeys the some integral equation. This can be solved numerically or analytically in some regions. And we can estimate the free energy of the by averaging this is some right momentum of the energy, and this is some proportion distribution of the energy distribution. So this is the free energy of the modules, and we can estimate the effective central charge at the, for example, taking UV ring of the model, where L is pointing. So the UV effective central charge actually becomes flat free. So this is actually expected from the beta under agree with the effective central charge of the 6 buckets. So
well, it is a twist 6 buckets, but not the usual 6 buckets.
Twisted means that we have some twisted boundary condition on the spins. So that parameter L controls the twisting of the boundary. So
omega depends on L.
Omega. Yes, omega is the appearing in the omega depends on N. Omega defines the. So you want to understand the algebraic structure that behind the ODE correspondence. So maybe I'll explain. I start from the explaining some notation of the maybe some familiar with to the audience. But I will use this notation. So G is a simple real E algebra with the rank R, and H and E alpha is a basis, and alpha 1 to alpha R is a simple root of G, and alpha 0 is the minus of the highest root. The highest root is expanded bounded in terms of the simple root. It's called the Coxeter numbers. And some of the Coxeter number is called the Coxeter number. And we also use a wide vector, which are some of the fundamentals. So this is the basic notation. So, and what is affine algebra? So, affine algebra is, as some system, is extended simple roots. We add the simple roots to the ordinary simple real algebra. So, the two types of the affine algebra. One is the untwisted, just a simple extension of the just adding. And the twisted one is just constructed from the untwisted affine algebra by holding the linking diagram. So some roots are identified. I'm not sure explain this, but some interesting properties of the affine algebra, some relation between the twisted and untwisted affine algebra. So that is called the Lagrange dual, or Goddard-Knight-ODE dual in the physics. So that relates the simple roots and simple corroots that are exchanged to each other. So for simply raised cases, that is the Lagrange dual is the same, and the for non-simply raised cases, the twisted affine algebra is related to the untwisted by taking a corroot. So we generalize the Lukyanov the model arguments. This is a sign order models, but we consider generalize it to the affine product field series based on some general affine theory. So the Lagrangian is some exponential interaction, but we have, this is the affine case, we have the contribution of the additional simple roots, alpha z. So we have some equation motion of this Lagrangian, which is the affine to the field equation. So due to some additional term, plus to the total equations, which is based on the simply algebra. So without the potential term, the theory is shown to be conformal invariant. This is, for example, taking a review theory. But with this potential term, remember the Sinus-Gordon theory, it becomes a massive theory. So the equation motion changes under the conformal transformation. But we do the conformal transformations and make it some different equations. So we do the conformal transformation and also shift the scalar field by this amount of quantities. So we have some modified affine. So P is defined by this Jacobian conformal transformation by with this power of the Coxeter.
Modified affine to the equation are still integrable.
Yes, that's right. So we have a Lux formalism. So modified affine to the equation can be expressed as a zero curvature condition of the affine algebra. Then, so this is rather complicated, but some generator with exponential term, we can show that this zero curvature condition gives the modified affine. So that is integral. And in this case, we can use some additional parameter for the spectral parameter. And we define associated with this zero flux equations, we can define some linear differential equations for this parameter. we can also arbitrariness to define the gauge transformation to rewrite this linear problem. We can take some certain gauges to simplify the problem. So let's take the modified Sinch-Gordon equation. In this case, we have just single scalars, and Pz is also we have a very simple cases that Pz will be like this. So this this is situations set up that we can get the desired ODE correspondence equation. Zero curvature conditions we write the connections in terms of like this, if like this, expressed like this, and this is modified Sinch-Gordon.
S is additional parameter.
Yes, yeah, S is addition, complex parameter. So we can think about the solution of the most modified Sinch-Gordon equation at the in the region that is large, when Z is large or Z. So for the case of the magnitude of Z is going to infinity, so the problem is so this Z to them term is major contribution to that thing. So we can compete this Z to M and to phi for large rho. Then we have this kind of logarithmic phi shape for the solution of the modified Sinch-Gordon. But for rho is going to 0, we have no restriction to capture that. So we have imposed some boundary condition arbitrarily in the rho when the rho is going to 0. And so we can introduce some new parameter L for the boundary condition are good. So we solve the linear problem. We consider the linear problem with this boundary condition for the solution of the modified affine equation.
So but there's a constraints between L and M.
M.
The last point. Is there a constraint on L?
Yeah. No, just some parameter.
But in the equation, the second and third term are continuous. If you go
Yeah, that's in that case is this to Z to the M is not major contribution. Only the distance is things.
Right.
And, yeah.
it's always negative now.
Yeah, and so we can choose that that two exponents are just vanish at the origin. So that will have some. We have also we can that two only two exponents are just competing, such that the subleading term will cancel to each other. That's the way of construction. Then we have the solution, the linear problem. We consider the linear problem and asymptotic solution. So we can find some very similar phase rotation that have this of this linear system. And so actually maybe it's not so important in that talk. So there we have some subdomain solutions at infinity and some solution at the rho is going around the rho is going to 0. So we have defined the similar Q functions satisfied some delta integration. We can also construct T functions and phi functions which they satisfy the delta twice. Not that I showed that statement. So then we can go to the modified Sinch-Gordon equation to the ODE by taking something. So first I take the right cone limit, where the z bar is going to z. So in that limit, the linear system is going to be a holomorphic differential equation of z, single holomorphic differential equation. And if we take some certain gauge transformation, that the connection, the holomorphic connection problem, linear problem makes it simpler. So that such that the connection is take that. So it is easy to write down the linear system. This is a first order rank 2 linear differential system. We can write it in a second order single differential, ordinary differential equation. So in the context of Soliton, it is called mirror transformation. And we have this kind of simulation. And we will take a further conformal limit where the z is going to 0, and also spectral parameter is going to infinity, but this variable x and e is going to be fixed. So essentially, z is going to 0. We have sitting around the center of the complex plane. That phi is going to behave the L times log x. So that means that this linear system ODE is going to become the ordinary differential equations that with potential and with argument sector. This is exactly the same ordinary differential equation that was considered by Korean. Okay. So we have some scheme to, we can generalize it in arbitrary affine algebra. So we have this kind of picture. Then if we start from the affine equation based on the Lagrange dual of the affine algebra. So we have some linear problem, and so we can have some beta equations for by solving this linear problem. So we have beta equation for the integral model associated with the G hub, not G hub check. So that corresponding to the master integral models. But if we take the conformal limit, we will have some ODE. This is generalization of the Dorian Tateo, and we can have some ODI correspondence. So that gives some massless integral models, some certain CFT we will have this correspondence. So some interesting feature is some Lagrange duality. This was done by Rock and Masoero, Raimondo, and Daniel. The modified equation, affine equation for the Lagrange dual corresponds to the G-type beta, which was classified by the So this is some explicit ODE for some cases. But this is other things. So the remaining time, I will talk about the ODI correspondence and the relation to the Arrhenius-Douglas. So the Arrhenius-Douglas theory is a kind of strong coupling N-equal-2 superconformal is very important. So since it contains some mutually non-local monopole and dion coexist and become massless at some fixed point, it can be no default frame for the, it can not Lagrangian in some, we have no frame to Lagrangian in local, as a local Lagrangian. So there's no microscopic Lagrangian distribution. So it's very difficult to study. So the curve of the, so what is has a low, it's defined as a low energy effective theory of the N-equal-2. So the Seiler-Witten curve of the Arrhenius-Douglas theory is somehow realized by degeneration of the original Seiler-Witten curve in some cases. So for example, so SUSY, pure angle series, cyber-wisdom curve. This is some genus 2 hyperelliptic linear service. But we can decompose it in some two torus. The one torus is going to be very small compared to the other torus. So the BPS spectrum associated with small torus becomes giving a massless BPS. So it's a bit non-local to each other. That will give the IPS service. So this is a very typical example studied by in 1997. So some explicit construction of the RBS Douglas theory is one way to construct the. This is a special case of the RBS Douglas theory associated with the AD type theory. So the cyber-Witten curve is related to that is the spectral curve of the actually appears some affine to the appears again in this setup. So for AD type cyber-Witten theory, its cyber-Witten curve is obtained by the spectral curve of the periodic affine to the. It's just a one-dimensional reduction of the affine to. So it takes like this form. You denote some scale parameter of that circuit, and the WG is some sort of superpotential of the lambda into cell in two dimensions. For A type case, it's just a polynomial. Cyber-Witten differential is two dimensions. So now the RBS Douglas point is realized at the some Coulomb branch variables are said to be almost Z, but the top maybe R in this way it should be R plus 1. So this should be some constant proportion to the scale parameter. Taking some appropriate scaling variables, rho, which is equal to the some